Hello everybody again. In the previous video, we went ahead and manually tried to find the minimum value for this function. And 5x squared plus 3y squared, it was quite straightforward to see that the optimal happens at the point 0, 0, when x is 0 and y is 0. And we are using the gradient descent method to find that recursively. So the method tells us to first start with the gradient. So the derivative of this with respect to, let me put this, okay. So the derivative of our function with respect to x turned out to be just 10x from our previous video, if you remember it. There you go. And similarly, the derivative, of our function with respect to y, that's just 6y. All you do is just, sorry for that, you just take the derivative with respect to y. Yeah. All right, so the steps. So this is just a column header. No worries, no calculations in this column. Let me just put a, sorry for that. There we go. Highlight it. Here we go. All right, so to begin with, I need to write a formula for my function. So let's write that formula now. It's basically the formula that I just wrote, but I need to use cell references. So 5 times, I need to take this and then square it, plus 3 times, take that y value and then square it. Notice that this is our starting point, 4, 5 in the example that we did previously. In the previous video, I should say. So as a result, 10x will be just 10 times the x value. And this is equal to 6 times the y value. And in the previous video, again, we solved these values. We found those values of 40 and 30. Now we need to derive the new values of x. So if you call this starting point at x0 and y0, so these will be x1 and y1. Right, so it's our first iteration, and at the end of the first iteration, let me make a note here. So that will be x1 comma y1 in a sense. All right, so that's what will come out of that at the end of the first iteration. All right, so let's write out the formula for this. It's basically starting with x0 plus the step size, which is this number over here, times the gradient, which is this number. Does that make sense? Press enter. We'll do the same thing here. You start with y0 plus the step size times the gradient. There you go. So our goal is to find that step size just the way we did it in the earlier video, in the previous video. And in the previous video, I used optimization, right? I took the derivative, set it equal to 0 to find the step size, and I believe it came out as 0.12. The first step was 0.12, but it had to be in the minus direction. Let's see if we can get a similar result here. So how are we going to do that? Our goal is to, by changing this, to optimize this. Does that make sense? To find the value of this. So what we will do is these two, the x1 and y1, they depend on d. If you look at inside this formula, they refer to that value of d. So by changing the value d here, for instance, if I put it 0.1, you guys can see how this one is changing its value. You guys see that? All right. So what I will do then is the following. Instead of, I think I should correct my formula. Instead of referring to the initial givens, I will refer this formula to the past, to the new ones. All right, so let me just go ahead and make that change. So I should rather refer to x1 here. So that's a typo. Oops, x1 I should say. There we go. And then this one should refer to y1. Okay, so I made my correction for this value. Okay, let's do it again. So these are the new values again, because as d is right now 0. But if I change d to 0.1, for instance, these two values will change. And as a result, you see how the f value changed. So the question is, how can I change this so that I minimize the f function here? Wow, this looks like very promising, right? How about minus 0.2? No, it went up again. Do you guys see that? How about minus 0.15? Oh, it's still down, but I think minus 0.1 was the best. How about minus 0.11? Ah, that's even better. Can you guess what will be the d which will make it this number the smallest? Of course we know it. It is minus 0.12. We did it in the previous video. Let's find it ourselves using the features of Excel now. And it is very convenient optimization tool called Solver. So if you go to data ribbon in Excel, there's this data solver function. If you don't see it here, what you should be doing is you should go to file again, and from file you should go to I believe account, here account, and no, not account, sorry, you should rather go to options, I should say, sorry, options at the bottom. Yes, options. Okay, there you go. From options you go to add-ins, and from add-ins you go to the bottom here where it says Excel add-ins, say go, and make sure analysis tool pack is checked. The others, oh sorry, analysis tool pack and especially solver add-in, so that's the thing we want. So press OK. All right, now that I know I have solver, I'm directly starting the optimization now. Using solver, my goal is to, okay, going back, I think, so I just delete this. I want to minimize this. So let me change this to minimum by changing the value of the steps function. And that's pretty much it. This is an unconstrained optimization. All I should just say is solve now. All right, it didn't seem to work. Let me check again. Okay, so let's go ahead and now do the optimization. So we have, we will use solver like I said. So we go to data ribbon, go to solver, and in solver first select the function itself, which is this one, then select the steps function. We want to minimize, make sure minimization is clicked here, and finally make sure this is unchecked. Make unconstrained variables non-negative. We don't want to do that. It should be any step function, any direction. All right, and just say solve. There you go. Hey, this is pretty good. In our case, what we did is our step function was of the size, because I did up to 2 decimal places of accuracy, right? So, but this one is more accurate. And these are the new locations of x1 and y1. Now in the second step, I will carry those two values. Let me just carry those two values here. And this is the y value. Now, starting with x1 and y1 now, I will like to find x2 and y2. X2, y2. There you go. All right, so let's just do it. So all I actually will do is I will just drag this formula. So it is pretty much on. So, and then drag these as well. There you go. We are going to pretty much drag these as well, because the same formulas will just apply. Each time, all I need is just to recalculate these step functions. That's it. So repeatedly use, and then we will also drag these as well. There you go. So for instance, let's do this 10 times. All right, so the second attempt, so, and over time we will find x3, y3, and so on, right? So here it will give me the x3, comma y3. If I do it 10 times, ultimately I'm expecting, the goal is to get to 0 0, right? So we should be as close as possible to 0 0, because we know that that's where the optimal value happens. The minimum value in this case will happen. Let's see if we can get to 0 0 or something close to 0 0. All right, so here we do the same thing again. We go to data ribbon. Our goal is solver. So this time we want to optimize this guy, right? So this is the second iteration. This is the value by changing this one, this step value, the size of the, and then this is unchecked. That's good. And I'll say okay. Awesome. So now we have, hey, this is the same we found earlier when we did in the previous video. We found minus 0.13 as well. And this is our new point. Just keep repeatedly doing this. That's it. That's how easy this whole thing is to find it. So all you go to data, go to solver. This time we want this one, which is referring to this cell over here, and by changing this number, and then press OK. There you go. Do you guys see how we are getting closer and closer to the desired result? One thing here, that dragging business, when I dragged it, it dragged all the formulas with the associated cell references. Do you guys see that? So for instance, if I go here, F2, you will so this one will be the partial derivative with respect to this one. So for instance, if I go down the row, oops, F2, you guys see that it's still the same references. I think it's pretty straightforward. Let's do it here as well. Yeah, it's the same thing. Awesome. So let's go to the next step. We will do the same thing here. Oh, sorry, not equal to. We will use solver, right? So data, go to solver, and this time the objective is this one. Minimize that. Minimize. It's clicked. Subject to by changing this one. That's it. There's no other constraint. There you go. The step functions are always negative direction, which is good. And we're getting closer and closer to the point 0, 0. Remember, ultimately, in the last entry here, we want to get something very, very close to 0, 0. That's our goal, right? Yeah, so let's do it again. Here, data, solver. We want to optimize. Oops, I can barely see it now. This one. Subject to, sorry, by changing this step function here, solve it again, boom, say okay. Wow, so we are getting really, really close. Probably we won't even have to go that far, right? In fact, let me just increase the decimal place of accuracy so you guys can better see. So let's just turn it into a number and then have as many decimal places as possible. Let's see how far we can go. All right, so the next one, go to data ribbon, and then we go to solver, and instead of the 7th, I think this one is the 8th, and then the step is the 8th as well, and then just say solve. That's it. Like, oh wow, so it's getting really, really close to 0, 0, 0, 0, 0, right? So pretty good. Let me do it 3 more or 4 more times. I'll keep doing it until it doesn't changes anymore. Minimum, so this one should be the 9. That cell, this one is a 9, and solve it. All right. Wow, super, super close. Okay, next. Solver, minimum. So this one is a 10 now. This one is a 10. Sometimes when it is extremely close to 0, it just stops working. So let's see if that's gonna happen or if we can get ever closer to 0. So solver again. This time we are going to do it with 11, I11. All right. Well, you see, it's not letting me do anymore. Do you see? It's extremely close to 0. It's telling me that we need to stop right there. It gave me a 0. Either because I already reached the destination, but these are extremely tiny numbers, like 4.5 raised to the times 10 raised to the power minus 5. So this is really tiny. Do you guys see that? So here, because let me actually go ahead and do that so you guys can convince yourself this is the case. Oops, the other way. Look at that. When I, like, if I were to go one more step, yeah, you see that? So in up to 4 decimal place, we are already literally at 0 for the x value, and y value is 0.0001. But okay, so let's add one more. So if you were to calculate it up to 5 decimal places of accuracy, so that would be it. So you would have stopped here. Why? Because the number does not change anymore. So we would have stopped right here. So stop the algorithm here. Does that make sense? And this is our guess. So we would, so which is, I mean, extremely close to 0, 0, that we, the point value x equals 0 and y. And look at the value of your function. It is literally 0. So let me just go ahead and convert it into number and add more decimal. There you go. I mean, so technically, we found the desired answer up to 1, 2, 3, 4, 5, 6, 7, 8. So, well, 7 decimal place of accuracy, which is 1 or 2 in 10 millionth. So we are making an error of 2 in 10 millionth, and we achieved that in 8 iterations. That's it. We stopped the algorithm after 8 steps. This is really good. And it just took us a few minutes to do that. The machine did everything. If it's up to us, it's very difficult to find these, because each time we take the derivative, set it equal to 0. We just did the first 2 manually, and it was already pretty difficult, but machines, Excel can do it pretty fast. All right, so that's pretty much it. So I hope you guys enjoyed it. If you want, let me just go ahead and show how the picture looks like on Wolfram Alpha. So there you go. So on Wolfram Alpha, all I do is, let me just revise this. So it was 5x squared plus, I think we said 3y squared, right? So let's just enter. Yeah, so 5x squared plus 3y squared. This is how the shape looks like in the third dimension, and it has a global minimum right at that point 0 and 0, x value 0, y value is 0, right? It looks like a bowl. Do you guys see that? And that's it. So if you guys want, it already gives you the partial derivative, so you can make use of it as well during the problem set solution. So it's pretty good. In fact, if you just write next to it minimum, it's pretty good. So Wolfram Alpha will give you the desired results, but there's a lot of websites like this. So it already gives you the point where the absolute minimum happens, right? So it happens at the point 0, 0. So this is where the absolute minimum is. And if you want, we can say partial derivatives. Let's see if it gives us the result. I won't be so, yeah, there you go. So it gives you the oh no, not that way. Okay, so I think it's giving us with respect to x, yeah, it's treating as implicit differentiation. So this is another concept that we can have a look at another time. So no, that's not good. So but at least what it did is it gave us in the original. So when you don't write it, so it automatically gives you the partial derivatives, which is good. All right, so 10x here and 6y here, the ones that we did. All right, so I hope this was useful. Hope to see you guys in our next lecture.